Welcome friends to this new lecture of soil science and technology, and in the previous lecture we talked about what is soil colloid and what are the different classes of soil colloids, and then we distinguish between the inorganic soil colloids and organic soil colloids. We talked about what are the different types of inorganic soil colloids, and then we started about silicate clays, and we distinguished silicate clays into several categories, starting from nesosilicates, then sorosilicates, then cyclosilicates, inosilicates, then phyllosilicates and tectosilicates, and we specifically started talking about phyllosilicates because that represents soil clay minerals, and we started talking about the basic building blocks of phyllosilicates, that is silica tetrahedra. We talked about their structure, and we talked about how they linked with each other to form a silica tetrahedral sheet. And then we also talked about aluminum octahedron and how aluminum octahedral sheets are formed, and then how they sandwich between one octahedral sheet sandwich between two tetrahedral sheet to form a 2:1 structure, and what is 1:1 structure, what is unit cell, and what is what is interlayer, what is layer, and what is what is crystal, and then what are the different types of planes. So we stop there and let us start and let us go from here, and in today's lecture we will be discussing in details about mineral structure of different clay minerals. So before going to the structure of the clay minerals, let us discuss what are the major sources of charge. Now we will be discussing these sources of charges in details in our our forthcoming lecture, but let me tell you that there are two major sources of charges which develop within the clay minerals. So one of them is isomorphous substitution, and in case of isomorphous substitution, what happens, one element fills the position of another element having similar size. So you can see here here there is a tetrahedra, silica tetrahedra, which is basically neutral, and then one silica in the tetrahedra is basically replaced by, in the tetrahedral sheet, basically this is a tetrahedral sheet, and one silica in the tetrahedral sheet is getting replaced by aluminum, which is having the similar sizes as that of silica, and as a result of that there is an excess of negative charge. So because silica that +4, aluminum is +3, and O4 means -8. So here +7 -8, that means -1. So there is a negative charge generation. So as a result of this type of substitution, we call it isomorphous. Iso stands for similar, morphous stands for size. So since silica and aluminum has almost similar size, this aluminum can substitute this silica. Not only that, another major prerequisite for this type of substitution is that there should be difference in valency of 1, not more than 1. So you can see +4 valency of silica is getting replaced by +3 valency of aluminum. So this is called silica. This is an example of isomorphous substitution in case of tetrahedral layer. However, in case of octahedral layer, you can see aluminum is getting replaced by magnesium because both of them are having the similar size. So remember that in case of silica tetrahedral layer or silica tetrahedral sheet, silica gets replaced by aluminum, whereas in case of octahedral layer, aluminum generally got replaced by either magnesium or iron. So these are the this isomorphous substitution is one of the major source of charges which develop in the clay minerals, and that's why clay is reactive. There are other there are other sources of charges also. We will discuss them later on. So let us move ahead and see in details this isomorphous substitution. You can see here in this tetrahedra 3 cations, obviously -3 stands for 3 oxygen group, and one of the so we are getting -3 because one of their minus charge is getting shared with the adjacent silica, and here in the trioctahedral layer, obviously you remember the tetrahedral layer where all the 3 octahedral positions are filled by cations. Now, in case of trioctahedral layer, if you remember, the octahedral positions are basically dominated by magnesium, because it has 2 valency plus 2. So, you can see this is plus 2 plus 2 plus 2. So, it is plus 6. So, here we are getting a net charge of 0. However, when we are replacing also, I mean here also there is a dioctahedral layer where we are getting the total net charge of 0. However, if in this dioctahedral sheet, if we replace one aluminum with one magnesium, then you can see there is a generation of net 1 negative charge. So, this is an example of dioctahedral with isomorphic substitution. You can see what are the different ions which can replace among themselves. So, silica get almost already replaced by aluminum, and this type of silica replacement by aluminum occurs in tetrahedral sheet, whereas in case of octahedral sheet you can see generally aluminum get replaced by either iron or magnesium or sometimes zinc. So, so these are some examples of isomorphic substitution or isomorphous substitution. So, in summary, what are the basis for distinguishing crystalline silicate clays? Obviously, based on the numbers and combination of structural units, we already know that how these crystals are formed, and each crystals are formed with in the form of layers, and obviously there are 2 general categories, 1:1 and 2:1. We have already discussed this, and obviously by the number of cations in the octahedral sheet, trioctahedral structure and dioctahedral structure, we have already covered this. Then size and location of layer charge, and then type of bonding of layers. Obviously, remember that there are different types of bonding occurs between the layers. Obviously, ionic bonding is the most ionic bonding has the most strength, followed by hydrogen bonding and then van der Waals force, which is very weak in nature. And obviously, we can distinguish clay crystalline silicate clays based on the presence or presence of a cationic interlayer, like in case of fine grained mica or illite. We will discuss that in later. So, mineralogical organization of silicate clays, we already covered that in the last lecture, that is 1:1 type of silicate clays and 2:1 type of silicate clays. So, I am not going to discuss that in details. Obviously, in case of 2:1 type of layer, one octahedral layer is sandwiched between 2 tetrahedral sheet, and so this is the basic organizational difference between this 1:1 and 2:1 type of layer. Now, let us start with 1:1 silicate clays. So, you can see here basically in this type of silicate clays, its layer consists of 1 tetrahedral and 1 octahedral sheet held together by apical oxygen atom. Obviously, you can see there are certain planes of atoms. Obviously, here you can see hydroxyl and aluminum, which are snugly fitted in the holes, and also oxygen and silica in between. So, there are several layers of atoms, and if we see a 2-dimensional display, we can see obviously there will be hydroxyl plane followed by an aluminum plane, and then again oxygen and hydroxyl plane followed by silica plane and then oxygen plane. So, this is an example of 1:1 layer of 1:1 type of clay, because there is only one silica tetrahedral sheet and one aluminum octahedral sheet. What is the major clay mineral? Kaolinite is the most common 1:1 type of clay. This is most prevalent, one of the most prevalent 1:1 type of clay. And remember that this kaolinite is the major ingredient of the porcelain, and this kaolinite got its name because it was first invented in the Kaolin province of China, and it is synthesized under equal concentration of aluminum and silica. And this is the actual silica structure. You can see these are basically hexagonal flex. These are basically hexagonal. These individual layers are hexagonal in shape, and this is how this kaolinite will look under the electron microscope. So, let us go ahead and see there's some properties of kaolinite. Obviously, in case of kaolinite, there is no isomorphous substitution. Remember that it is very important. In case of kaolinite, we cannot see any isomorphous substitution. So, due to the absence of isomorphous substitution, obviously there is a very little chance of development of negative charge. There is very little chance of development of negative charge at their surface, and as a result of that, they are very nutrient poor, because no cationic nutrient can absorb at the surface because of this low low negative charge development. And obviously, it has got no shrink swell potential because of hydrogen bonding between the adjacent layer. So, let me show you what does that mean. So, if we consider one tetrahedral 1:1 kaolinite, obviously. So, this will be silica tetrahedra and this will be aluminum octahedra. So, similarly, another adjacent layer will consist the similar repeating unit. So, it will be silica tetrahedra followed by aluminum octahedra. So, in the aluminum octahedra, as you can see at the base of aluminum octahedra, obviously there will be hydroxyl ions, and just below these aluminum hydroxyl ions you will see the oxygen plane. So, if you consider this is as a layer, single layer, and you consider another repeating layer here, obviously there will be hydroxyl atoms here. So, here we are getting oxygen and here there are adjacent hydroxyl. So, obviously there will be a bond formation between this oxygen and hydroxyl. This is the hydrogen bonding or hydrogen bond, and due to the presence of this hydrogen bond between these two adjacent layer, this 1:1 type of layer clay or kaolinite cannot show any swelling shrinkage property, okay, because of this hydrogen bonding between the two repeating layers. So, that is the reason that this kaolinite cannot show any swell shrinkage properties, and obviously it is a product of acid weathering, and this is how a kaolinite will look like. It is white in color. Pure kaolinite is basically white in color, and this is the interlayer structure. Obviously, this is the layer structure of kaolinite. Obviously, you can see the d-axis spacing. That means the spacing between, if we consider this is a plane of layer of atom, and obviously the adjacent or the very next similar plane layer of atom, the distance is called d-axis spacing or d spacing, and this d spacing in case of kaolinite is 0.74 nanometer. So, again the d-axis spacing in case of kaolinite is 0.74 nanometer or 7.2 angstrom. So, less cation exchange capacity owing to hydrogen bonding, and relatively it is less, and this kaolinite shows relatively less plasticity, stickiness and cohesion. Okay. So, we have finished the kaolinite. I hope. Then let us go ahead and see what are 2:1 type of clays. Well, as the name suggests, 2:1 is basically 2 silica tetrahedral sheet linked with 1 octahedral sheet, and you can see 4 major groups of 2:1 type of clays. One is expanding clay and the non-expanding clay. Among the expanding clay, you can see smectite and then vermiculite, and however, in case of non-expanding clay, there are fine grained mica or illite and then chloride. So, these are 4 I would say these are 4 major types of, these are 4 major types of 2:1 type of clays, and we will discuss them in details, not groups, but the types. So, let us start with the smectite. So, in case of smectite, obviously there will be in case of smectite there is a high amount of isomorphous substitution, and they are mostly negatively charged because of this high amount of isomorphous substitution. and as a result of interlayer molecules and interlayer water and cations, they are subjected to shrinking and swelling when owing to loosely bound oxygen to oxygen and oxygen cation bonding. We will see it in a bit. And remember that it also shows high plasticity, stickiness and cohesion owing to high expansion. So, the one of the major example of this smectite is Montmorillonite, and this smectite type of clay can be found in the black cotton soil of India, especially in Maharashtra region, where you will see the development of cracks and swell during the during the monsoon as well as in dry season. I will show you. So, let us see. Okay, the Montmorillonite. Montmorillonite is a 2:1 type of smectite obviously, and layer charge originates from the substitution of magnesium for alumina in the octahedral sheet. Remember, these are nutrient rich and they show very high shrink soil capacity, and they are very unstable under low pH and high moisture, and this is how the pure Montmorillonite will look like. So, let us see the structure of Montmorillonite. So, this is structure of the Montmorillonite. Obviously, the d axis spacing, that is, if we consider this is a oxygen plane and this is another repeating oxygen plane. So, the distance is d axis spacing. So, similarly, if we consider this is a silica plane and here is also silica plane. So, the distance between these two similar repetitive layer is basically the d axis spacing. So, do not get confused about the d axis spacing. So, in case of Montmorillonite, the d axis spacing varies from 1 to 2 nanometer, and because in the interlayer space there is a high amount of water molecules and miscellaneous cations. Why there are high molecules and interlayer cations? Because you can see this is a structure of Montmorillonite. Obviously, there will be hydroxyl, there will be oxygen atoms and there will be silica atoms, followed by then hydroxy, then aluminum and magnesium, because aluminum and magnesium because of isomorphous substitution, and the similar repeating layer you can see here. So, obviously, due to the variable spacing between these two repeating layer, there will be chance for exchangeable cations to enter, and obviously, there will be hydrated exchangeable cation inside this interlayer space. And as a result of this, there will be variable distance, or there will be variable d axis spacing. As you can see, it is varying from 1 to 2 nanometer. And remember that isomorphous substitution is occurring in the octahedral layer. So, again, in case of Montmorillonite, the isomorphous substitution occur in the octahedral layer, and as a result of this substitution, there will be generation of the negative charge repulse themselves. As a result, there will be obviously different hydrated exchangeable cations enter into the interlayer space, and as a result there will be variable spacing, and as a result of this variable spacing they will show shrink and swell property, because in the dry season obviously the interlayer water will evaporate and these two layers will collapse to each other and then it will shrink, and during the wet season or monsoon season the water will go inside and then it will create the swelling. So, this is how Montmorillonite shows the swelling and shrinkage property. So, this is how Montmorillonite looks like under electron microscope, and you can see this is a very common black cotton soil in India, and you can see this is an example of Vertosol. Obviously, you know about the Vertosol. So, Vertosols are like that. I mean, they are dominated by this Smectite and Montmorillonite, and they shows these deep, these deep cracks during the dry season because of this swelling and shrinkage property. Okay. So, let us go to the another one, vermiculite. Remember that it is a weather mica product where potassium ions between the molecular sheets are replaced by magnesium ions, and they have highest cation exchange capacity. We will discuss what is cation exchange capacity later on among all the clays, and less swelling capacity than smectite, but more than kaolinite. and remember they are very nutrient rich and stable under low pH. Now, this is important, less swelling capacity than smectite, but more than kaolinite. We will discuss why. So, again this is the structure of vermiculite. You can see this is the rightmost structure is basically the electron micrograph of vermiculite, and in the left one you can see the actual the structure of vermiculite. The interlayer d-axis spacing varies from 1 to 1.5 nanometer, and obviously in the interlayer space there will be dominance of water molecules, magnesium and other ions. Okay. So, this is about vermiculite. So, let us see what we have. The next group is mica group. Mica group is basically represented by this mineral called illite, and illite will look like fibrous. Illite will show fibrous nature under electron microscope, and in case of illite obviously there will be only isomorphous substitution in the tetrahedral layer. In the tetrahedral layer, silica 4 or silica atom get replaced by aluminum atom or aluminum ions. Silica get replaced by aluminum, and as a result of that there will be a high net negative charge, although the interlayer space will be dominated by potassium ion which get absorbed in the interlayer, and as a result of that they will lock the structure. These potassium ions are very small in size. As a result of that there will be very less space in the interlayer, and as a result there will be non-expanding, there are non-expansive, and they are fairly nutrient poor in nature. So, this is a structure of illite. Obviously, you can see the isomorphous substitution only occurring in the tetrahedral layer, and obviously whatever negative charge develop is getting satisfied by this interlayer K plus, and K plus is very small. As a result of that they are almost collapsed, and as a result of that they are very much tightly bound, and as a result they are collapsed. Only the d-axis spacing is 1 nanometer, and that is why these are non-expanding in nature. Another name of illite is fine grained mica. Alright. So, the final one, chloride. Chloride is basically also having the similar structure as the other 2:1 type of mineral. However, in the interlayer space there are iron or magnesium occupy. There will be an interlayer octahedral sheet which will be either occupied by iron or either occupied by magnesium. We talked about that in our last class. Obviously, when there will be magnesium hydroxide interlayer, that will be considered as brucite layer. When there will be aluminum hydroxide interlayer, that will be considered as gibbsite layer. So, hydroxy octahedral sheet in the interlayer space, and they obviously due to the presence of this hydroxy octahedral interlayer space, they shows restricted swelling due to the log interlayer structure. They are nutrient poor, and they are very much common in sedimentary rocks and the soils derived from them. So, this is the structure of the chloride. You can see obviously they are almost similar than that with the 2:1 type of mineral. However, in the interlayer space there is a hydroxide sheet based on the dominance of hydroxide. Based on the dominance of the cations of the hydroxide, they are named differently. Obviously, either it is magnesium hydroxide or aluminum hydroxide. The interlayer or d-axis spacing is 1.4 nanometer, and as a result of the presence of this hydroxide sheet, they are locked structure and they have low nutrient capacity. So, let us see a visual comparison between all the different types of clay minerals or major clay minerals. Remember that there are hundreds of different clay minerals. However, we are only focusing on 4 to 5 major ones. So, let us see what are their visually, how can separate them. So, you can say let us start with the simplest one. So, the kaolinite is the simplest one. It is non-expanding and non-swelling. It is 0.5 1:1 type of layer with the d-axis spacing of 0.7 nanometer, followed by Montmorillonite. Montmorillonite is 1 to 2 nanometer interlayer or d-axis spacing, and water molecules consist, the interlayer space is dominated by either water molecules or miscellaneous cations. And in case of vermiculite, the interlayer space is dominated by water molecules and magnesium and other ions, and the d axis spacing is little bit lower than that of Montmorillonite. It is 1.1 to 1.5 nanometer. And then fine grained mica or non expanding illite, obviously due to the presence of interlayer potassium, they are locked in nature, and the d axis spacing is also very less, followed by this chloride, which is 2:1, 1:1. By the way, we call chloride as 2:1:1, because 2:1 we already know, and 1 stands for another magnesium or aluminum hydroxide sheet, and these are also non expanding or minimum swelling. So, this is a visual comparison between these major clay minerals. So, let us see how clay mineralogy and weathering patterns are linked. So, this is very interesting diagram. So, you know that secondary minerals or clay minerals basically forms from weathering of the primary minerals. So, let us see what are the sequence of different secondary minerals when they are generating from the primary minerals. So, if we see the primary minerals, these are the first or precursor of secondary minerals or clay minerals. So, at first from the primary minerals, obviously there will be the formation of illite or chloride. Okay. And in the next step, obviously the interlayer potassium of the chloride, interlayer potassium of illite will be replaced, because as the weathering is going on, all the interlayer ions will be getting replaced by other ions which are present in the soil environment. Obviously, you will see that illite will be converted to vermiculite, because the only difference between illite and vermiculite is the interlayer potassium. So, when the interlayer potassium get replaced, they will be ultimately converted to the vermiculite. Similarly, in case of chloride, when the magnesium will be replaced, magnesium will be weathered, or magnesium will be removed, ultimately it will be producing the vermiculite. And from vermiculite, when the interlayer magnesium will be further reduced or removed, ultimately it will produce the smectite. From the smectite, remember that there is a 2:1 type of mineral. So, we are having more dominance of silica tetrahedra than aluminum octahedra, 2:1 So, there will be further weathering will remove the silica further, ultimately will be producing 1:1 type of kaolinite, and further an extreme weathering condition, there will be further removal of silica, ultimately producing the iron and aluminum oxide. So, you can see in case of young and weakly weathering soil, you will see the dominance of illite and chloride, and in case of intermediate weathering, you will see the dominance of smectite and sometimes vermiculite, and obviously in case of strong weathering condition, you will see the dominance of kaolinite and iron and aluminum oxides. So, this is how weathering and intensity of weathering can help in changing one clay mineral to another clay mineral. Okay, this is the we have covered the basic structure of clay minerals, and we have discussed about their d axis spacing and all these important parameters which are and then we made the visual comparison between different clay minerals, and we distinguish them based on their d axis spacing and also based on the interlayer cations and interlayer other molecules. So, let us wrap up here, and in the next lecture we will be finishing this this silicate clays, and then we will go ahead and see what are the different sources of charge, which are different sources of charges which basically develop within the clay mineral. So, till then, thank you.